If someone asked you to point where the solar system sits inside the Milky Way, you'd probably picture a flat spiral seen from above with a little dot labeled, "You are here," about 2/3 of the way out. Almost every diagram you've ever seen shows it that way. But here's what nobody tells you. That picture is dangerously misleading. The Milky Way isn't a flat image, it's a 3-dimensional structure with depth, thickness, and layers. And our solar system doesn't just sit at some generic spot along a spiral arm. It occupies a very specific position inside a very specific structure. And that position has consequences most people never think about. Tonight, we're going to find out where we actually are and why the real answer is far stranger than the simple diagram. Before we go any further, if you find this kind of deep exploration interesting, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Now, let's begin. Let's start with something you've probably seen 100 times. A picture of the Milky Way. You know the one. A beautiful spiral galaxy viewed from above with graceful curving arms and a bright glowing center. Somewhere along one of the outer arms, there's a little arrow or a dot with the words, "You are here." It's a clean, elegant image, and it makes you feel like you understand where you are in the galaxy. But that image is a lie, not a complete lie. The basic shape is roughly correct. The Milky Way is a spiral galaxy and the solar system is located in the outer portion of the disk. But that top-down diagram leaves out almost everything that actually matters about our position. It flattens the galaxy into 2 dimensions. It makes the spiral arms look like solid highways. It gives you no sense of depth, no sense of thickness, no sense of the enormous 3-dimensional volume we actually inhabit. And it creates an illusion of understanding where no real understanding exists. To truly know where the solar system sits inside the Milky Way, you have to throw away that flat picture entirely and build a new one from scratch. A picture with depth, with structure, with layers, and with scale that will challenge everything you think you know about our cosmic address. So let's do that. Let's start with the most basic question of all. What is the Milky Way? Physically, not as a picture, not as an idea, but as a real object in space. The Milky Way is a barred spiral galaxy. That means it's a vast collection of stars, gas, dust, and dark matter organized into a roughly disc-shaped structure with spiral arms extending outward from a central bar. When astronomers say barred spiral, they mean the galaxy has a long, straight bar of densely packed stars running through its center, and the spiral arms extend from the ends of that bar rather than from the center itself. This bar is made of older, redder stars and stretches roughly 27,000 light years from end to end. It's not a solid object, of course. It's a dense concentration of stars moving along elongated orbits that create the appearance of a bar shape when viewed from outside. The galaxy contains somewhere between 100 billion and 400 billion stars. That range is enormous, and the reason for the uncertainty is simple. We're inside the galaxy. Trying to count the stars in the Milky Way from our position is like trying to count all the trees in a forest while standing in the middle of it. You can see some of them clearly. Many more are hidden behind other trees, obscured by fog, or simply too far away to make out. Dust and gas block our view in many directions, especially toward the galactic center. And dim stars, which make up the majority of the stellar population, are extremely difficult to detect at large distances. The best current estimates suggest somewhere around 200 billion to 300 billion stars. But the number could be higher or lower, depending on how many faint red dwarf stars exist in regions we can't easily observe. But stars are only part of what the Milky Way contains. Between the stars, there are vast clouds of gas and dust. These clouds are made mostly of hydrogen, the simplest and most abundant element in the universe, along with helium and trace amounts of heavier elements like carbon, oxygen, and silicon. Some of these clouds are cold and dense, the places where new stars are born. Others are hot and diffuse, heated by radiation from nearby stars or by the shock waves from supernova explosions. The total mass of gas in the Milky Way is estimated at roughly 10 billion to 15 billion times the mass of the Sun. That's a lot of material, but it's actually only a small fraction of the galaxy's total mass. The dust is even less massive, making up only about 1% of the mass of the gas. But don't underestimate it. Interstellar dust is incredibly effective at blocking visible light. Even a thin layer of dust spread across thousands of light years can completely obscure what lies behind it. This is why the center of our galaxy is invisible to the naked eye and to ordinary optical telescopes. The dust between us and the galactic center absorbs the visible light, hiding the dense concentration of stars that lies at the heart of the Milky Way. Then there's dark matter. This is the invisible substance that makes up most of the galaxy's total mass. We can't see dark matter directly because it doesn't emit, absorb, or reflect light. But we know it's there because stars in the outer regions of the galaxy orbit faster than they should, based on visible mass alone, requiring additional unseen mass to explain their motion. The Milky Way's dark matter is distributed in a roughly spherical halo that extends far beyond the visible disk of stars. This dark matter halo might stretch out to 600,000 light years or more from the galactic center. The total mass of the Milky Way, including dark matter, is estimated at about 1.5 trillion times the mass of the Sun. And the vast majority of that mass, perhaps 85 to 90%, is dark matter. The stars, the gas, the dust, everything you can actually see, it's just a small fraction of what's really there. The galaxy is like an iceberg. The visible part is impressive, but it's only a hint of what lies beneath the surface. Now, let's talk about shape, because the shape of the Milky Way is crucial for understanding where we sit inside it. The most prominent feature is the disk. This is the flat, thin structure that contains most of the galaxy's stars, gas, and dust. When you see pictures of spiral galaxies viewed edge-on, they look like thin flying saucers. A wide, flat disk with a central bulge. The Milky Way looks similar. The disk is roughly 100,000 to 180,000 light years across, depending on where you define the edge. Recent studies, including data from the Gaia spacecraft, suggest the disk might be larger than previously thought, possibly extending up to 200,000 light years in diameter when you include the faint outermost regions. But here's the crucial part. While the disk is enormous in diameter, it's surprisingly thin. The main disk of the Milky Way is only about 1,000 to 2,000 light years thick. Think about that ratio. A structure that spans 100,000 light years or more across, but only 1,000 to 2,000 light years from top to bottom. If you scaled the Milky Way down so that its diameter was the length of a football field, the disk would be thinner than a sheet of paper. It's incredibly flat. This extreme thinness is important because it means the galaxy has a genuine vertical dimension. There's an above and a below relative to the disk. Stars and gas are concentrated in this thin plane, but the density drops off as you move away from the midplane in either direction. The midplane is the geometric center of the disk's thickness, and it's the reference point astronomers use when talking about positions above or below the galactic plane. At the center of the disk sits the galactic bulge. This is a dense, roughly spherical concentration of stars that spans roughly 10,000 light-years across. The bulge contains a mix of old and young stars, though it's dominated by older, redder stars. The stellar density in the bulge is much higher than in the outer disk where we live. If you could somehow transport yourself to a planet near the galactic center, your night sky would be completely different from what we see on Earth. Instead of a few thousand visible stars scattered across the darkness, you'd see tens of thousands, or even hundreds of thousands of stars. So many that the night sky would glow with a continuous carpet of light. There would be no true darkness between the stars. The sky would be a dazzling, overwhelming blaze in every direction. At the very center of the bulge sits Sagittarius, a star, the supermassive black hole. This black hole has a mass of about 4 million times the mass of the Sun. Despite its enormous mass, the black hole itself is relatively small. Its event horizon, the boundary beyond which nothing can escape, is only about 17 times the diameter of the Sun. That sounds big, but in galactic terms, it's a point. A tiny gravitational monster sitting at the heart of a vast structure. Sagittarius. A star is relatively quiet right now. It's not actively consuming large amounts of material, but evidence suggests it was much more active in the past, and it will likely become active again in the future when gas or stars wander too close. Beyond the disk and the bulge, there's the stellar halo. This is a roughly spherical region surrounding the disk, extending out to perhaps 130,000 light-years or more from the galactic center. The halo contains old stars and globular clusters, dense spherical collections of hundreds of thousands or even millions of ancient stars. These globular clusters orbit the galactic center on highly elongated paths that take them far above and below the plane of the disk. The halo stars and globular clusters are among the oldest objects in the galaxy. Many formed more than 12 billion years ago, when the Milky Way was still in the early stages of assembly. They're relics from a time before the disk had fully formed, when the galaxy was a more chaotic collection of smaller structures merging together. Studying halo stars is like studying fossils. They tell us what the galaxy was like in its youth. And then, surrounding everything is the dark matter halo. This extends even farther than the stellar halo, possibly out to 600,000 light-years or more. It's the invisible scaffolding that holds the entire galaxy together. Without dark matter, the Milky Way as we know it couldn't exist. The stars would orbit too slowly to maintain the galaxy's structure. The disk would fly apart. Everything depends on this invisible mass that we can detect only through its gravitational effects. So, that's what the Milky Way is. A thin disk of stars, gas and dust, roughly 100,000 to 200,000 light-years across, and only 1,000 to 2,000 light-years thick. A central bulge of dense, mostly older stars. A sparse stellar halo of ancient stars and globular clusters. And a massive dark matter halo enveloping everything. It's a three-dimensional structure with distinct layers, distinct regions, and distinct properties at different locations. It's not a flat picture, it's a volume. Now, where is the solar system in all of this? The answer that most people know is approximately correct. We're about 26,000 light years from the galactic center. That puts us roughly in the middle of the disk's radial extent, about halfway between the center and the outer edge. Some sources say we're about 2/3 of the way out, and that's a reasonable approximation depending on where you define the edge of the disk. If the disk extends to about 50,000 light years in radius, then 26,000 light years puts us just past the halfway point. If the disk extends to 75,000 or even 100,000 light years in radius, then we're closer to 1/3 or 1/4 of the way out. The exact fraction depends on how you measure the disk's extent, which is itself an uncertain number. But even this simple statement that we're 26,000 light years from the center is more interesting than it first appears, because 26,000 light years is an enormous distance. Light, traveling at about 300,000 kilometers per second, the fastest speed possible in the universe, would need 26,000 years to travel from the galactic center to where we are. When we observe the region around the galactic center, we're seeing it as it was 26,000 years ago, when humans were still living in the last ice age. Agriculture hadn't been invented yet. There were no cities, no writing, no civilization as we know it. The light that left the galactic center when those ancient humans were hunting woolly mammoths is only now reaching Earth. And the galactic center itself is relatively close compared to the full extent of the galaxy. Stars on the far side of the Milky Way, 80,000 or more light years from us, are so distant that their light has been traveling since before modern humans existed as a species. But here's where the standard picture starts to break down. When people hear that we're 26,000 light years from the center, they imagine a flat disk with our position marked on it, like a pin on a map. They picture the galaxy from above, see the spiral arms, locate us in one of the arms, and think they understand our position. But this top-down view misses something fundamental. It misses the vertical dimension entirely. The Milky Way's disk has thickness. It has a top and a bottom, and within that thickness, the density of stars, gas, and dust varies. The midplane of the disk, the geometric center of its thickness, is where the density is highest. As you move upward or downward away from the midplane, the density gradually decreases. Stars become more spread out. Gas clouds thin. The environment changes. Our position within this vertical structure matters enormously, and it's something the flat diagram never shows you. The solar system doesn't sit exactly at the midplane of the disk. It's slightly above it. Current measurements suggest we're about 50 to 80 light years north of the galactic midplane. That might sound like a trivial offset, and in galactic terms, it is small. The disk is 1,000 to 2,000 light years thick, so being 50 to 80 light years off-center is a minor displacement. But it's not zero, and it's not permanent. The sun oscillates above and below the midplane as it orbits the galaxy. We'll explore this oscillation in detail later, but for now, the key point is this. Our position in the galaxy isn't just a spot on a flat map. It's a point in three-dimensional space, defined not only by our distance from the galactic center and our position relative to the spiral arms, but also by our height above or below the midplane. The flat diagram gives you one coordinate. Our real position requires three. The disk itself isn't perfectly flat either. Recent observations have shown that the outer regions of the Milky Way's disk are warped. The disk bends upward on one side and downward on the other, like a slightly twisted, or curved surface. This warping has been known for decades from observations of hydrogen gas in the outer galaxy, but more recent data from the Gaia spacecraft has confirmed that the stellar disk is warped too. The cause of this warping is still debated. It might be due to gravitational interactions with satellite galaxies like the Large and Small Magellanic Clouds, or it might be related to the galaxy's dark matter halo being slightly misaligned with the disk. Whatever the cause, the warp means that the disk isn't a perfectly flat plane. It's a gently curved, slightly twisted structure, especially in its outer regions. At our position, about 26,000 light-years from the center, the warping is minimal. We're close enough to the center that the disk is still quite flat in our neighborhood. But if you lived on a planet farther out, say 50,000 or 60,000 light-years from the center, the warping would be noticeable. The midplane of the disk in your region might be displaced by hundreds or even thousands of light-years from where it would be if the disk were perfectly flat. There's another aspect of the Milky Way's structure that the flat picture completely fails to convey, and that's the sheer density of material between us and the galactic center. When you look at the top-down diagram, the center of the galaxy looks like a bright spot that you could simply look toward and see. In reality, the galactic center is completely invisible in visible light from our position. It's hidden behind enormous quantities of interstellar dust. The dust particles are tiny, mostly comparable in size to the wavelength of visible light or smaller. Individually, each grain is almost nothing, but accumulated across thousands of light years, this dust absorbs and scatters visible light so thoroughly that we can't see through to the galactic center. The galactic center is one of the most interesting and dramatic places in the entire galaxy, a region of intense stellar density, powerful magnetic fields, and a supermassive black hole. And yet we can't see any of it with our eyes or with ordinary optical telescopes. It took the development of infrared and radio astronomy in the 20th century to finally peer through the dust and study the galactic center. Infrared light, which has longer wavelengths than visible light, can pass through dust much more easily. Radio waves with even longer wavelengths are essentially unaffected by dust. By observing the galaxy at these wavelengths, astronomers were able to map the galactic center for the first time, discovering the supermassive black hole, the dense concentration of stars surrounding it, and the complex structures of gas and magnetic fields in the central region. This brings up another critical point about our position. Where we sit in the galaxy determines what we can observe about the galaxy. And what we can observe has shaped our entire understanding of what the Milky Way is. For centuries, astronomers could only observe the galaxy in visible light. They could see the band of the Milky Way stretching across the night sky, a glowing river of light created by the combined glow of billions of distant stars in the disk. But they couldn't see through the dust to understand the galaxy's full structure. They didn't know there was a central bar. They couldn't count the spiral arms or determine their positions accurately. They couldn't even measure the size of the galaxy reliably, because dust obscured the distant stars that would have served as distance markers. It was only in the early 20th century that astronomers began to realize how large the Milky Way actually is and where we sit within it. In 1918, the American astronomer Harlow Shapley studied globular clusters, those dense balls of ancient stars that orbit in the galaxy's halo. By mapping the positions of globular clusters, Shapley realized they weren't evenly distributed across the sky. They were concentrated in one direction toward the constellation Sagittarius. This told him that the center of the galaxy was in that direction, and that the sun was far from the center. His measurement of the distance wasn't perfectly accurate, but the key insight was revolutionary. The sun was not at the center of the galaxy. We were off to one side, in the outer regions of a vast structure. Before Shapley, many astronomers assumed the sun was near the center of the stellar system. After Shapley, we knew we were peripheral. This was another in a long series of cosmic demotions. First, Copernicus showed that Earth wasn't at the center of the solar system. Then Shapley showed that the sun wasn't at the center of the galaxy. Later, Edwin Hubble showed that the Milky Way wasn't the entire universe, but just one galaxy among many. Each discovery pushed us further from any privileged position, revealing that we're not central, not special, not uniquely placed. We're in a specific spot, and that spot happens to be in the outer half of a thin disk in a large spiral galaxy. But that specific spot, that precise position inside the galaxy, turns out to be far more interesting and far more consequential than the simple top-down diagram suggests. Because where we sit affects everything. It affects what we see when we look at the night sky. It affects how much radiation we're exposed to from nearby stars. It affects the density of interstellar material around us. It affects the probability of catastrophic events like nearby supernova explosions. Our position in the galaxy isn't just an address, it's a set of physical conditions, a specific environment with specific properties that have shaped the history of our planet and the evolution of life on it. We're going to explore that environment in detail. We're going to look at the spiral arms and understand what it means to be in the Orion Arm rather than one of the major arms. We're going to examine the three-dimensional structure of our location, our height above the midplane, the oscillation of the sun through the disk, and the local bubble of hot gas that surrounds us. And we're going to discover that our position in the galaxy, far from being a random or uninteresting detail, is one of the most important factors in the story of life on Earth. But first, you need to let go of that flat picture. The one with the neat spiral arms and the little arrow saying, "You are here." That picture served its purpose. It gave you a rough idea of our location, but it's a simplification so extreme that it borders on misleading. The real Milky Way is a complex, layered, three-dimensional structure with depth, thickness, and variation. And the solar system's position within that structure is defined not by a single point on a flat map, but by a precise location in three-dimensional space, a location with specific physical properties that make it unlike almost any other point in the galaxy. The Milky Way isn't a diagram, it's a place, a vast, deep, textured, evolving place, and we live inside it. Not on the surface of a picture, but embedded within its structure, surrounded on all sides by the stars, gas, and dust of the galactic disk. Every direction you look, you're looking through the Milky Way. Every star in the night sky is a neighbor in this structure. The glowing band of light that stretches across a dark sky is the disk itself. Seen from the inside, billions of stars too distant to resolve individually, blending together into a river of faint luminescence. You are inside the Milky Way right now, not looking at it from outside, not hovering above it with a bird's eye view. You're embedded in it like a single cell inside a living body, surrounded by structure in every direction. And understanding that, really understanding it, is the first step toward knowing where we truly are. Now, let's talk about spiral arms, because this is where most people's understanding of our position in the galaxy goes seriously wrong. When you look at that familiar top-down diagram of the Milky Way, you see beautiful, well-defined spiral arms curving outward from the center. They look solid. They look like permanent structures, like highways carved into the disk of the galaxy. And somewhere in one of those arms, there's a tiny dot representing our solar system. The implication is clear. We live in a spiral arm the way you might live on a street. The arm is a fixed thing, a place, and we're inside it. But that's not how spiral arms work. Not even close. Spiral arms are not solid structures. They're not made of a fixed set of stars that stay together as the galaxy rotates. They're something far stranger and far more interesting than that. And understanding what they actually are is essential to understanding where the solar system really sits. The best way to think about spiral arms is as waves, specifically density waves. This idea was proposed in the 1960s by the Chinese-American astronomers Chia Qiaolin and Frank Xu, and it revolutionized our understanding of galaxy structure. Before the density wave theory, astronomers had a serious problem. If spiral arms were made of fixed groups of stars, they should wind up and disappear relatively quickly. The inner parts of the galaxy rotate faster than the outer parts. This is called differential rotation. Stars closer to the center complete their orbits faster than stars farther out, just as planets closer to the sun orbit faster than planets farther away. If the spiral arms were made of the same stars all the time, this differential rotation would wind the arms tighter and tighter with each orbit, like twisting a piece of string. Within a few galactic rotations, the arms would be wound so tightly that they'd essentially disappear. The galaxy would become a featureless disk. But that clearly hasn't happened. The Milky Way is roughly 13 billion years old. The Sun has completed roughly 18 to 20 orbits around the galaxy in the 4.5 billion years since it formed. If the arms were winding up, they should have vanished long ago. Yet they persist. The density wave theory explains why. A density wave is a pattern that moves through the disk of the galaxy independently of the stars themselves. Think of it like a traffic jam on a highway. Cars enter the jam from behind, slow down, bunch together, and then eventually exit the front and speed up again. The individual cars pass through. They don't stay permanently. But the jam itself persists, maintaining its shape even though the individual components are constantly changing. Spiral arms work the same way. The density wave creates a region of slightly higher gravitational attraction in the disk. As stars orbit the galaxy, they pass through this region. When they enter the wave, they slow down slightly, bunching together. This creates a region of higher stellar density, which is the visible spiral arm. After a while, the stars pass through and continue on their way, speeding up again as they leave the denser region. The arm persists because new stars are constantly entering from behind, replacing the ones that have left. The arm is a wave, a pattern, not a fixed collection of objects. But the density wave does more than just bunch up existing stars. It also compresses the gas and dust in the disk. When interstellar gas enters the density wave, it gets squeezed. The compression increases the density of the gas, and when gas becomes dense enough, it can collapse under its own gravity to form new stars. This is why spiral arms appear so bright and blue in images of spiral galaxies. They're not just regions where existing stars are bunched together. They're regions where brand new stars are being born. And the brightest, most massive new stars, The hot blue giants that dominate the visual appearance of spiral arms are incredibly luminous, but also incredibly short-lived. They burn through their hydrogen fuel in just a few million years, then explode as supernovae. These massive blue stars never make it out of the spiral arm. They're born inside the arm, they live their brief, brilliant lives inside the arm, and they die inside the arm. By the time they would have had a chance to move through and exit the density wave, they've already exploded. This is why spiral arms look so prominent. They're lit up by the brightest, youngest stars, the ones that were just born from the compressed gas. The older, dimmer stars that make up the majority of the galaxy's stellar population are spread more evenly throughout the disk. They've had time to move through multiple spiral arm passages and are distributed more uniformly. The spiral arms are like the crests of waves in an ocean. They're the places where things are happening, where gas is being compressed, where stars are being born, where massive stars are exploding. Between the arms, things are quieter. The stars are older, dimmer, and more spread out. The gas is thinner and less compressed. Fewer new stars are forming. Now, how many spiral arms does the Milky Way have? This is a harder question than you might expect. Remember, we're inside the galaxy, embedded in the disk, surrounded by dust that blocks our view in many directions. Mapping the spiral arms from inside the galaxy is like trying to map the layout of a city while standing on one street corner with fog in every direction. You can see your immediate surroundings clearly, but the farther you look, the more obscured things become. Despite these challenges, astronomers have identified several major spiral arms. The most prominent are the Scutum Centaurus arm and the Perseus arm. These are considered the two primary arms of the Milky Way, the ones that extend from the ends of the central bar. But how do we know any of this? How do you map the spiral arms of a galaxy you're inside of when dust blocks your view in most directions and you can't step outside to take a photograph? This is one of the great achievements of modern astronomy, and it's worth understanding how it was done because it reveals just how hard-won our knowledge of our own galaxy really is. The first major breakthrough came from radio astronomy. In 1951, astronomers detected the 21-centimeter emission line of neutral hydrogen gas. Hydrogen is the most abundant element in the interstellar medium, and it emits radio waves at a very specific wavelength when its electron flips its spin orientation. This radio emission passes through interstellar dust almost completely unimpeded, which means astronomers could detect hydrogen gas across the entire galaxy, regardless of how much dust lay in the way. By measuring the Doppler shift of this emission, how much the wavelength was stretched or compressed by the motion of the gas, astronomers could determine how fast the gas was moving toward or away from us. Combined with models of how the galaxy rotates, these velocity measurements could be converted into distances. This allowed astronomers to build the first rough maps of the Milky Way's spiral structure in the 1950s and 60s. The maps were crude and had significant uncertainties, but they confirmed that the Milky Way had spiral arms and gave the first estimates of their positions. Later techniques refined the picture enormously. Astronomers used maser emissions, naturally occurring microwave laser beams produced by molecules like water and methanol in star-forming regions, as precise distance markers. These masers are bright enough to be detected across the entire galaxy. By using a technique called very long baseline interferometry, which combines radio telescopes thousands of kilometers apart into a single virtual telescope, Astronomers could measure the positions and distances of these mesas with extraordinary precision. The bar and spiral structure legacy survey, known as BSL, used this method to map star-forming regions across the Milky Way, producing some of the best spiral arm maps we have. Then came the Gaia spacecraft, launched by the European Space Agency in 2013. Gaia measured the precise positions, distances, and motions of nearly 2 billion stars in the Milky Way using parallax. The slight shift in a star's apparent position as Earth moves around the Sun. By mapping these stars in 3 dimensions, Gaia revealed the spiral structure of our local region with unprecedented clarity, showing the Orion Arm's true extent and confirming its significance as a genuine galactic structure rather than a minor spur. The Scutum Centaurus arm begins at one end of the bar and wraps around toward the far side of the galaxy. The Perseus arm begins at the other end of the bar and extends outward in the opposite direction. Beyond these 2 main arms, there are several secondary or minor arms. The Sagittarius arm, sometimes called the Sagittarius-Carina arm, lies between the Scutum Centaurus arm and the Sun's position. The Norma arm is closer to the galactic center. And then there's the arm that matters most to us, the one we actually live in. For a long time, astronomers referred to our local spiral structure as the Orion spur or the Orion Cygnus arm. The word spur suggested it was a minor offshoot, a small bridge of material connecting 2 major arms rather than a significant arm in its own right. The Orion spur was thought to be a relatively short, minor structure sitting between 2 much larger and more important arms, the Sagittarius arm on the inside and the Perseus arm on the outside. This made our position seem rather unimpressive. We weren't even in a real spiral arm, just a little spur between 2 actual arms. But more recent observations have changed this picture significantly. Studies using radio telescopes to map the positions of star-forming regions and giant molecular clouds, as well as data from the Gaia spacecraft, measuring the distances and motions of millions of stars, have shown that the Orion Arm is larger and more significant than previously thought. It's not just a minor spur, it's a substantial arm segment, possibly rivaling some of the major arms in length and importance. Some recent studies suggest the Orion Arm might extend for more than 20,000 light years, which would make it comparable in length to portions of the major arms. Whether you call it the Orion Arm, the Orion Spur, or the local arm, it's a real, significant structure in the galaxy's spiral pattern. It contains active star-forming regions, massive molecular clouds, and young stellar clusters, all the hallmarks of a genuine spiral arm. So where exactly is the solar system within this arm? We sit near the inner edge of the Orion Arm, closer to the Sagittarius arm side than to the Perseus arm side. The center of the Orion Arm is roughly in the direction of the constellation Cygnus, while the Sagittarius arm lies roughly in the direction of the constellation Sagittarius toward the galactic center, and the Perseus arm lies in the opposite direction, outward from us. The distance between the major arms in our region of the galaxy is roughly 6,500 to 13,000 light years, depending on which arms you're measuring between and exactly where along the arms you measure. The Orion Arm sits in this interarm gap, not centered perfectly between the 2 major arms, but positioned somewhat closer to the inner Sagittarius arm. This means our immediate neighborhood in the galaxy is characterized by the properties of the Orion Arm. We're in a region of moderate stellar density, surrounded by a mix of old and young stars with active star-forming regions scattered throughout our arm, but not overwhelmingly close to us. The nearest major star-forming region, the Orion Nebula, is about 1,344 light-years away. It's visible to the naked eye as the fuzzy middle star in Orion's sword. Inside it, hundreds of new stars are being born from collapsing clouds of hydrogen gas. Some are massive blue giants that will live only a few million years before exploding. Others are small red dwarfs that will burn steadily for trillions of years. The nebula is a stellar nursery and one of the most prominent features of our local arm. Other notable star-forming regions in the Orion Arm include the Carina Nebula, roughly 7,500 light-years away, and the Eagle Nebula, about 7,000 light-years away, and famous for the Hubble Space Telescope's iconic Pillars of Creation image. These regions are all part of the same spiral structure that we inhabit. They're our neighbors in the Orion Arm, fellow members of the same galactic structure. But now let's go deeper. Let's look at our even more immediate surroundings, because within the Orion Arm, the solar system occupies a very specific local environment that's unlike most of the interstellar medium. It's called the local bubble, and it's one of the most important features of our cosmic neighborhood. The local bubble is a vast cavity in the interstellar medium, a region roughly 1,000 light-years across, where the density of gas is much lower than average. The interstellar medium, the gas and dust that fills the space between stars, typically has a density of about 1 atom per cubic centimeter in the general disk of the galaxy. That doesn't sound like much, and it isn't by everyday standards. The air you're breathing right now has about 25 quintillion molecules per cubic centimeter, but 1 atom per cubic centimeter is the normal background density of interstellar space. Inside the local bubble, the density drops to about 1/10 of that, or even less. The gas is also much hotter than the surrounding medium, with temperatures reaching roughly 1 million degrees. This might sound paradoxical. How can the gas be extremely hot but extremely thin at the same time? The answer is that temperature in physics isn't quite the same as what we feel as hot and cold. Temperature measures the average energy of individual particles. In the local bubble, each individual atom is moving very fast, which means it has high energy and therefore a high temperature. But there are so few atoms per cubic centimeter that the total amount of heat energy in any given volume is actually very low. If you were floating in the local bubble, you wouldn't feel hot. You'd feel nothing because there simply aren't enough particles to transfer meaningful amounts of energy to your body. The local bubble was carved out by supernova explosions. Sometime between 10 and 20 million years ago, a series of massive stars in our general neighborhood exploded at the end of their lives. These explosions sent powerful shockwaves through the interstellar medium, sweeping up the gas and dust and pushing it outward, creating a cavity of hot, low-density gas. The walls of the local bubble are denser than the interior, compressed by these ancient shockwaves. Several other nearby bubbles exist as well, some overlapping with the local bubble, creating a complex, interconnected network of cavities in the interstellar medium. Recent research has shown something remarkable about the local bubble. A study published in 2022 used 3-dimensional maps of nearby molecular clouds and star-forming regions to show that nearly all the major star-forming regions within about 500 light-years of the Sun are located on the surface of the local bubble. The Orion star-forming complex, the Taurus molecular cloud, the Ophiuchus cloud complex, the Lupus clouds, all of them sit on the shell of compressed gas that forms the bubble's wall. The supernovae that created the local bubble compressed the surrounding gas, and that compressed gas became the raw material for new generations of stars. The very act of destroying the previous interstellar environment seeded the next generation of star formation. The solar system sits inside this bubble, not on its wall. We're in the interior, surrounded by hot, thin gas, relatively far from the dense molecular clouds where new stars are forming. This is a somewhat unusual position. Most stars in the galaxy are either in or near these denser regions of the interstellar medium. Being inside a large cavity like the local bubble means we're in a relatively protected environment, shielded from some of the denser interstellar material that could interact with the solar system's outer boundary. This brings us to an interesting question. What would the night sky look like if we were in a different part of the galaxy? Because our position shapes everything we see when we look up, and understanding this helps us appreciate just how specific our cosmic address really is. If you moved the solar system to the center of the galaxy, near Sagittarius, a star, the night sky would be almost unrecognizable. The density of stars near the galactic center is thousands of times higher than in our neighborhood. Instead of seeing a few thousand stars scattered across the sky, you'd see hundreds of thousands. The sky would glow with starlight in every direction. There would be no truly dark patches. Constellations as we know them would be meaningless because the stars would form a nearly continuous carpet of light. Interstellar dust would be much thicker in some directions, creating dark lanes and patches against the glowing background. And the supermassive black hole, while invisible itself, would make its presence known through the intense activity around it. Stars orbiting close to the black hole at tremendous speeds. Clouds of gas being heated to millions of degrees. Occasional flares of radiation when material falls in. It would be a dramatic, violent, brilliant sky, unlike anything we experience from our quiet position in the outer disk. If you moved the solar system to a position deep inside one of the major spiral arms, say the Scutum Centaurus arm near a massive star-forming region, the sky would be different in another way. You'd see many more young, hot blue stars. The nebulae would be brighter and more prominent. Glowing clouds of gas lit up by ultraviolet radiation from nearby massive stars. But you'd also be exposed to much more danger. Massive stars die as supernovae, and being close to one when it explodes would be catastrophic. A supernova within about 50 light years could potentially strip away Earth's ozone layer, exposing the surface to deadly ultraviolet radiation. Being deep in a major spiral arm, surrounded by massive young stars, would mean living in a neighborhood where such explosions are relatively common. You'd have a more spectacular sky, but a more dangerous existence. If you moved the solar system far out into the galaxy's outer disk, beyond most of the spiral structure, say 60,000 or 70,000 light years from the center, the sky would be eerily sparse. There would be far fewer stars visible. The stellar density in the outer disk is much lower than in our region. The sky would be darker, with fewer points of light. The band of the Milky Way, that river of light that stretches across our sky, created by the combined glow of billions of distant stars in the disk, would appear narrower and fainter, because you'd be looking through less of the disk in most directions. You'd also be in a region with fewer heavy elements. Stars in the outer disk tend to have lower metallicity, meaning they contain less iron, carbon, silicon, and other elements heavier than hydrogen and helium. These elements are produced by previous generations of stars and their supernovae, and the outer disk has had fewer generations of star formation. With fewer heavy elements, rocky planets like Earth would be less likely to form. You might find yourself orbiting a star with a system of gas giants but few or no rocky worlds. From our actual position, about 26,000 light-years from the center, inside the Orion Arm, within the local bubble, the night sky is a specific thing shaped by exactly where we are. We see the band of the Milky Way stretching across the sky because we're embedded in the disk and looking along its length. The band is brightest in the direction of Sagittarius because that's toward the galactic center, where stars are most densely packed. It's fainter in the opposite direction, toward the constellation Auriga and beyond, because that's looking outward through the thinner, less populated outer disk. The dark patches and lanes you see in the Milky Way band are caused by interstellar dust clouds blocking the light of more distant stars. The Great Rift, a dark lane that appears to split the Milky Way in two from Cygnus to Sagittarius, is caused by a relatively nearby complex of dust clouds in our section of the Orion Arm. These dust clouds are only a few hundred to a few thousand light-years away, but they're dense enough to block the light from the billions of stars behind them. This is a direct consequence of our position within the disk. We're looking through dusty interstellar material, and that material shapes what we see and what we don't see. The individual stars visible to the naked eye are mostly within about 1,000 to 2,000 light-years of us. The brightest ones, like Sirius at 8.6 light-years, Vega at about 25 light-years, and Arcturus at about 37 light-years, are very close neighbors in galactic terms. Even Betelgeuse, one of the more distant naked-eye stars, at roughly 700 light-years, is still well within our local section of the Orion Arm. When you look at the night sky, you're seeing a tiny sample of the Milky Way's stars, the ones close enough and bright enough to be visible from within our local bubble. The vast majority of the galaxy's hundreds of billions of stars are far too distant and too faint to see individually. They blend together into the diffuse glow of the Milky Way band or remain entirely invisible, hidden behind dust or simply too far away for their light to register in your eyes. Our position between two major arms also means we have a relatively clear line of sight outward through the disk in certain directions. Between the spiral arms, the interstellar medium is thinner and less dusty. This gives us windows through which we can see more distant parts of the galaxy and even other galaxies beyond. The Andromeda Galaxy, about 2.5 million light-years away, is visible to the naked eye as a faint, fuzzy patch in the constellation Andromeda. This is only possible because our line of sight to Andromeda happens to pass through regions of relatively low dust density. If we were deep inside a major spiral arm, surrounded by thick molecular clouds, we might not be able to see Andromeda at all. We might not even know it existed until we developed infrared or radio telescopes capable of peering through the dust. Think about what this means. Our understanding of the universe, the discovery that other galaxies exist, the measurement of the universe's expansion, the realization that the cosmos is vastly larger than the Milky Way, all of this depended on our ability to see beyond our own galaxy. And that ability was partly a consequence of where we happen to sit within the galactic disk. If our local interstellar environment were dustier, if we were embedded in a dense molecular cloud or positioned deep inside a major spiral arm, the history of astronomy might have unfolded very differently. We might have discovered the true nature of the universe much later, or through entirely different methods. The Orion Arm, our home in the galaxy, is a genuine spiral structure with active star formation, molecular clouds, and young stellar clusters. But also a relatively moderate environment compared to the dense, chaotic major arms. We're not in the thick of things. We're in a neighborhood that's active enough to be interesting, but calm enough to be safe. The nearest star-forming regions are hundreds or thousands of light years away, close enough to study but far enough to pose no threat. The nearest massive stars that might explode as supernovae are at safe distances. The local bubble provides an additional layer of protection, a cavity of thin gas surrounding us, keeping denser interstellar material at bay. This position, this specific set of circumstances, is not something you can capture in a flat diagram with a dot and an arrow. It's a three-dimensional environment with specific physical properties. The density of the interstellar medium, the proximity to star-forming regions, the thickness of dust along various lines of sight, the distance to the nearest potential supernova threats, all of these are consequences of exactly where we sit within the Orion Arm and within the local bubble. Change our position by even a few hundred light years, and some of these properties would be different. Move us 1,000 light years, and we might be inside a molecular cloud, or on the edge of a major star-forming region, or exposed to radiation from nearby massive stars. Our exact position matters, and it matters in ways that go far beyond simply knowing which arm we're in on a flat map. The spiral arms of the Milky Way are not roads. They're not permanent structures. They're density waves, patterns of compression that move through the disk, triggering star formation and creating regions of enhanced stellar density. Stars pass through them over millions of years, entering and exiting the arms as they orbit the galaxy. The Sun itself has passed through multiple spiral arms during its 4.5 billion year life. It wasn't born in the Orion Arm. It was born somewhere else, probably in a different arm or in an interarm region, and it has drifted to its current position over billions of years of orbital motion. The Orion Arm is our current address, not our permanent home. And within that current address, we sit in a specific spot, near the inner edge of the arm, inside a large cavity of hot, thin gas created by ancient supernovae, surrounded by star-forming regions on the walls of that cavity, with relatively clear lines of sight outward through the disk in certain directions, with the galactic center hidden from our optical view by thick lanes of dust, with the great band of the Milky Way stretching across our sky as a reminder that we're embedded in a vast, thin disk of stars, gas, and dust. This is our neighborhood. Not a dot on a flat map, but a three-dimensional volume of space with specific properties that shape our sky, our environment, and our understanding of the universe. And there's even more to our position than the horizontal layout of spiral arms and interstellar bubbles, because the galaxy has a vertical dimension too. And what happens above and below the galactic plane is just as important as what happens within it. So far, we've been talking about the Milky Way mostly in terms of its horizontal layout. The disk, the spiral arms, the distance from the galactic center. We've located the solar system about 26,000 light years from the center, inside the Orion Arm, within the local bubble. But all of this has been essentially a two-dimensional picture. We've been looking at the galaxy from above, placing ourselves on the map like a pin on a flat surface. And while that's useful, it's incomplete, because the Milky Way isn't flat. It has thickness. It has a top and a bottom. And our position within that vertical structure is just as important as our position within the spiral arms. This is the dimension that almost nobody thinks about when they picture our place in the galaxy. But it changes everything. Let's start with the basics. The galactic disk, as we discussed earlier, is roughly 1,000 to 2,000 light years thick. That's thin compared to the disk's diameter of 100,000 to 200,000 light years, but it's still an enormous distance. 1,000 light years means that light traveling at 300,000 kilometers per second would need a full millennium to cross from the top of the disk to the bottom. The disk isn't a razor-thin plane. It's a slab, a vast, flat slab with real depth. And within that slab, things aren't uniform from top to bottom. The density of stars, gas, and dust is highest at the midplane, the geometric center of the disk's thickness. As you move away from the midplane, the density gradually decreases. Stars become more spread out, gas clouds thin. If you could somehow fly straight up from the midplane, perpendicular to the disk, you'd notice the star density dropping as you climbed. The change would be gradual at first, almost imperceptible over a few dozen light years. But by the time you'd traveled several hundred light years above the midplane, the difference would be obvious. The dense river of stars, gas, and dust that characterizes the midplane would be thinning out below you, and above you, the sky would be opening up into the sparser environment of the galactic halo. But the disk isn't a single uniform layer. Astronomers have discovered that it actually consists of two distinct components: the thin disk and the thick disk. The thin disk is the younger, denser, more concentrated layer. It contains most of the galaxy's gas, dust, and young stars. It's where star formation happens. The thin disk has a scale height of roughly 1,000 light years, or about 300 parsecs, which means the density of stars drops by a factor of about 2.7 for every 1,000 light years you move away from the midplane. Most of the stars you see in the night sky, including the sun, belong to the thin disk. The thick disk is older, puffier, and less dense. It extends to a scale height of roughly 3,000 to 4,500 light years above and below the midplane. The stars in the thick disk are generally older than those in the thin disk, with ages of roughly 10 billion years or more compared to the thin disk's mix of young and old stars. Thick disk stars also tend to have lower metallicity, meaning they contain fewer heavy elements like iron, carbon, and silicon. This makes sense because they formed earlier in the galaxy's history, when fewer generations of stars had lived and died and enriched the interstellar medium with heavy elements. The thick disk was probably formed through a different process than the thin disk. One leading theory is that the thick disk was created when the early Milky Way merged with smaller galaxies billions of years ago. These mergers heated up the existing thin disk, puffing it out and creating a thicker, more diffuse layer. The thin disk we see today then formed later, as new gas settled into the midplane and began forming a fresh, thin layer of young stars. The Sun belongs to the thin disk. Its composition, age, and orbital characteristics all mark it as a thin disk star. It has relatively high metallicity, meaning it contains a good amount of heavy elements, consistent with having formed from gas that had been enriched by several previous generations of stars. Its orbit around the galaxy is relatively circular and stays close to the midplane, both characteristic of thin disk membership. Much of what we know about the thin disk, the thick disk, and our precise position within them comes from the Gaia spacecraft. Beyond its contributions to mapping the spiral arms, Gaia revolutionized our understanding of the galaxy's vertical structure in ways that no previous mission could. Beyond its contributions to mapping the spiral arms, Gaia revolutionized our understanding of the galaxy's vertical structure in ways that no previous mission could. Its unprecedented stellar catalogue allowed astronomers to dissect the disk into its component layers with extraordinary precision. Before Gaia, the thin disk and thick disk were understood mostly through statistical studies of relatively small samples of stars in the solar neighborhood. Astronomers knew the two populations existed because stars near the sun fell into two groups with different scale heights, different ages, and different chemical compositions. But the details were uncertain. The boundary between the thin and thick disks was fuzzy. The exact scale heights were debated. The origin of the thick disk was poorly constrained. Gaia changed all of this by providing data on a scale that was previously unimaginable. With precise distances to hundreds of millions of stars, astronomers could map the density of stars as a function of height above and below the midplane across a large swath of the galaxy, not just in our immediate neighborhood. This confirmed the two-component structure and refined the scale heights. Gaia's velocity measurements revealed the distinct kinematic signatures of thin and thick disk stars, showing that thick disk stars move differently, with more random, less circular orbits. And Gaia's data, combined with ground-based spectroscopic surveys measuring the chemical compositions of millions of stars, confirmed that the thick disk is chemically distinct, older, and likely formed through a different process than the thin disk. Our understanding of the vertical structure we have been discussing rests heavily on this mission's contributions. Now here's where things get specific and fascinating. The solar system doesn't sit exactly at the galactic midplane, it's slightly above it. Current measurements place us approximately 50 to 80 light-years north of the midplane. North in this context is a convention. Astronomers define the North Galactic Pole as the direction perpendicular to the disk in the direction of the constellation Coma Berenices, and the South Galactic Pole is in the opposite direction toward the constellation Sculptor. When we say the Sun is north of the midplane, we mean it's slightly displaced in the direction of Coma Berenices relative to the geometric center of the disk. 50 to 80 light-years might sound like a lot in everyday terms. It's an enormous distance by human standards, far larger than anything we could hope to travel with current or foreseeable technology. But in galactic terms, it's tiny. The thin disk has a scale height of 300 to 400 light-years, so being 50 to 80 light-years off the midplane means we're well within the thin disk, close to its densest central region. We're not on the edge of anything. We're not near the boundary between the thin disk and the thick disk. We're firmly embedded in the thin disk, just slightly displaced from its exact center. But this displacement isn't permanent. This is one of the most remarkable aspects of our motion through the galaxy. Something that almost nobody outside of astrophysics ever hears about. The Sun oscillates up and down through the galactic midplane as it orbits the galactic center. As we discussed, the Sun doesn't just travel in a flat circle around the galaxy. Its orbit also carries it up and down through the disk over tens of millions of years. The mass concentrated in the galactic midplane, all the stars, gas and dust in the thin disk, creates a gravitational pull toward the midplane. When the sun is above the midplane, as it is now, this gravitational pull acts downward, decelerating its upward motion, eventually stopping it, and then pulling it back down through the midplane. Once it crosses the midplane and continues downward, the same gravitational pull now acts upward, decelerating its downward motion, stopping it, and pulling it back up. The result is a sinusoidal oscillation, a smooth bobbing up and down through the midplane that repeats over a regular period. The period of this vertical oscillation is estimated to be roughly 60 to 70 million years for one complete cycle. That means the sun crosses the midplane approximately every 30 to 35 million years. It goes from maximum height above the midplane down through the center, to maximum depth below the midplane, and back up to the center in about 60 to 70 million years. Then the cycle repeats. The amplitude of the oscillation, the maximum distance above or below the midplane that the sun reaches, is estimated at roughly 250 to 350 light years. This means the sun's vertical range extends well within the thin disk, but takes it from somewhat below the midplane to somewhat above it and back again over tens of millions of years. Here's where this gets genuinely interesting and even a little unsettling. Some researchers have noticed that this oscillation period, roughly 60 to 70 million years per cycle, or about 30 to 35 million years between midplane crossings, seems to roughly correlate with the periodicity of certain events in Earth's geological and biological history. Mass extinction events, large impact cratering episodes, and even some climate variations appear to show a rough periodicity of about 26 to 30 million years. This has led to a provocative hypothesis. Could the sun's vertical oscillation through the galactic disk be influencing conditions on Earth? The idea works like this. When the sun is near the galactic midplane, it's in the densest part of the disk. The concentration of interstellar gas, dust, and molecular clouds is highest here. Passing through or near a dense molecular cloud could gravitationally perturb the Oort cloud, the vast shell of icy bodies at the outer edge of the solar system. These perturbations could send comets raining into the inner solar system, increasing the impact rate on Earth. Additionally, the midplane is where most massive stars are concentrated, and therefore where supernovae are most likely to occur. Being closer to the midplane might expose the solar system to more nearby supernova events, which could affect Earth's atmosphere and climate through increased cosmic ray flux. When the sun is far above or below the midplane, it's in a less dense environment. The interstellar medium is thinner. There are fewer molecular clouds to perturb the Oort cloud. Supernovae are less common because massive stars are concentrated closer to the midplane. The environment is calmer, potentially safer. So the idea is that the sun's vertical oscillation creates a periodic cycle of danger and safety. Every 30 to 35 million years, as the sun crosses the midplane, the environment becomes more dangerous. The impact rate might increase, the cosmic ray flux might spike, and these periodic environmental stresses might correlate with periodic extinction events in Earth's biological history. This hypothesis is controversial. The correlations are suggestive but not conclusive. The geological and biological records are noisy, and detecting true periodicities in them is extremely difficult. Some studies find evidence for the correlation, others don't. The timing doesn't match perfectly, and there are many other factors that can cause extinction events, volcanic eruptions, climate changes, ocean chemistry shifts. that have nothing to do with the galaxy. But the mere possibility that our vertical position in the galactic disk could influence the history of life on Earth is a profound idea. It connects planetary biology to galactic dynamics in a way that most people never consider. It means our position in the galaxy isn't just an astronomical curiosity. It might be a biological factor, a variable that has shaped the evolution of life on our planet over hundreds of millions of years. Right now, the sun is slightly above the midplane and appears to be moving upward, heading toward its maximum displacement above the midplane. This means we're currently in a relatively safer part of our oscillation cycle, moving away from the dense midplane environment. But in roughly 15 to 20 million years, the sun will reach its maximum height, reverse direction, and begin falling back toward the midplane. And in about 30 million years, give or take, it will cross the midplane again, entering the denser region where the risks may be slightly higher. None of this is cause for alarm on human timescales. These cycles play out over tens of millions of years. The effects, if they exist at all, are statistical tendencies rather than sudden catastrophic events. But it's a vivid reminder that our position in the galaxy is not static. We're moving. Not just around the galactic center, but up and down through the disk, passing through different environments over time. Now let's look upward and downward from our position and consider what lies above and below the disk. Because the galaxy doesn't end at the disk's edges. Beyond the thin disk and the thick disk, there's the stellar halo, a vast, roughly spherical region that surrounds the disk and extends out to perhaps 130,000 light-years or more from the galactic center. The halo is a profoundly different environment from the disk. Where the disk is dense, flat, and full of gas and ongoing star formation, the halo is sparse, three-dimensional, and essentially dead in terms of new star formation. The halo contains very little gas or dust, and almost no new stars are forming there. The stars that exist are overwhelmingly old, many more than 10 to 12 billion years old, formed before the disk had settled into its current thin, flat structure. Many halo stars travel on highly elongated, eccentric orbits that take them far above and below the plane of the disk. Unlike disk stars, which orbit the galactic center in relatively orderly, nearly circular paths within the plane, halo stars plunge through the disk on tilted, stretched orbits. A halo star might spend most of its orbital period high above or far below the disk, then dive through the midplane at high speed, cross the disk in a relatively short time, and emerge on the other side to climb back out into the halo. These stars are like visitors from another era, ancient objects on wild orbits that intersect the plane where younger, more orderly disk stars like the sun reside. The most spectacular inhabitants of the halo are the globular clusters. These are dense, spherical collections of hundreds of thousands to millions of stars, gravitationally bound into compact structures typically about 100 to 300 light-years across. The Milky Way has roughly 150 to 200 known globular clusters, and there might be more that we haven't detected yet, hidden behind the dust of the galactic disk. Globular clusters are among the oldest objects in the galaxy. Most have ages of 10 to 13 billion years, meaning they formed when the universe itself was very young, within the first few billion years after the Big Bang. They're relics from the era of galaxy formation, surviving intact through billions of years of galactic evolution. Their stars are metal poor, containing much less iron and other heavy elements than younger stars like the Sun, because they formed from gas that hadn't yet been enriched by many generations of stellar nucleosynthesis. Globular clusters orbit the galactic center on highly inclined, eccentric orbits, carrying them far above and below the disk. Some reach heights of tens of thousands of light years above the midplane. When you look at the distribution of globular clusters in the sky, they're not concentrated along the Milky Way band like disk stars. They're spread across the sky, with a concentration toward the direction of the galactic center. This was the key observation that Harlow Shapley used in 1918 to determine the Sun's position within the galaxy. The globular clusters are centered on the galactic center, not on the Sun, proving that we're far from the center of the galaxy. If you could see the Milky Way from outside, edge on, you'd see the thin, flat disk stretching across your field of view, with the central bulge puffing out in the middle, and scattered around this disk, like bees around a hive. You'd see the globular clusters, orbiting at various distances and inclinations, some close to the disk and some far above or below it. The stellar halo, much fainter and harder to see, would extend as a diffuse glow surrounding the disk and bulge, fading gradually with distance. And beyond even the stellar halo, the dark matter halo would extend outward for hundreds of thousands of light years, invisible but gravitationally dominant, holding everything together. From our position inside the disk, we can't see the structure directly. We're embedded in the disk, looking outward through it. The dust and gas of the disk block our view in many directions, particularly toward the galactic center, but we can see above and below the disk relatively easily. When you look toward the north or south galactic poles, perpendicular to the plane of the disk, you're looking through the least amount of intervening material. The disk is thin, only about 1,000 to 2,000 light years thick, so your line of sight quickly passes through the disk and emerges into the much clearer halo and beyond. This is why deep observations of distant galaxies are often made in directions away from the galactic plane. Astronomers choose fields of view near the galactic poles, where the foreground contamination from Milky Way stars and dust is minimized, giving the clearest possible view of the distant universe. The Hubble Deep Field, one of the most famous astronomical images ever taken, showing thousands of galaxies in a tiny patch of sky, was deliberately pointed away from the galactic plane toward a region of very low foreground dust. The James Webb Space Telescope continues this tradition, making many of its deepest observations in directions where the Milky Way's disk doesn't interfere. Our position within the disk creates a kind of cosmic curtain in some directions and a clear window in others. This brings us to one of the most important consequences of our three-dimensional position in the galaxy. The galactic center, arguably the most interesting region in the entire Milky Way, is almost completely hidden from us in visible light. The center lies about 26,000 light years away in the direction of the constellation Sagittarius. Between us and the center lies an enormous amount of interstellar dust, accumulated across thousands of light years of disk material. This dust is so thick that it absorbs roughly 1 trillion times more visible light than it lets through. The galactic center is one of the most thoroughly obscured objects in the sky. For centuries, astronomers had no idea what lay at the center of the Milky Way. They could see the bright band of the Milky Way stretching across the sky, and they noticed it was brightest in the direction of Sagittarius, suggesting there was something particularly dense in that direction. but they couldn't see through the dust to find out what it was. It wasn't until the development of radio astronomy in the 1930s and 40s that astronomers began to penetrate this veil. Radio waves, with wavelengths far longer than visible light, pass through interstellar dust almost completely unimpeded. By observing the galaxy at radio wavelengths, astronomers could see through the dust and study the galactic center for the first time. What they found was remarkable. The galactic center is a region of extraordinary density and activity. Stars are packed thousands of times more closely together than in our neighborhood. Massive clouds of gas orbit the center at tremendous speeds. Powerful magnetic fields thread through the region, organizing the gas into filaments and arcs. And at the very center, holding everything together, sits Sagittarius A star, the supermassive black hole. Infrared astronomy added another window. Infrared light, with wavelengths longer than visible light but shorter than radio waves, can also penetrate interstellar dust much more effectively than optical light. Infrared observations revealed the individual stars orbiting close to the black hole, including the star called S2, which completes an orbit around Sagittarius A star every 16 years at speeds reaching roughly 2.5% of the speed of light. By tracking the orbits of these stars over decades, astronomers were able to calculate the mass of the black hole with extraordinary precision, about 4 million times the mass of the Sun. None of this would have been possible with visible light alone. The dust between us and the galactic center is simply too thick. Our position within the disk, 26,000 light years from the center with thousands of light years of dusty interstellar medium in between, meant that for most of human history, the most dramatic feature of our own galaxy was completely invisible to us. We could see its effects, the concentration of stars and the brightening of the Milky Way band in that direction, but we couldn't see the center itself. It took new technologies, new ways of seeing beyond visible light to reveal what was there. This is a profound consequence of our three-dimensional position. We're not just in the disk. We're looking through the disk toward the center, and the disk is full of material that blocks our view. If we were above or below the disk, in the halo, we'd have a much clearer view of the galactic center. But we'd also be far from the ongoing processes of star formation and galactic evolution that make the disk so interesting. We'd be in a stellar backwater, surrounded by ancient, slowly fading stars, with little gas, little dust, and little activity. Our position in the thin disk gives us a front row seat to the galaxy's ongoing life, but it also puts a curtain between us and the most dramatic show at the center. The full three-dimensional picture of our position is now coming into focus. We're about 26,000 light years from the galactic center, measured along the plane of the disk. We're inside the Orion Arm, a significant spiral structure between the Sagittarius and Perseus arms. We're within the local bubble, a cavity of hot, low-density gas carved out by ancient supernovae. We're roughly 50 to 80 light years above the galactic midplane, within the thin disk, currently moving upward in our vertical oscillation cycle. Below us, the disk extends another several hundred light years to its lower boundary. Above us, the disk thins out within a few hundred light years, giving way to the sparser thick disk and eventually the stellar halo. Behind us, toward the galactic center, 26,000 light years of dust and gas block our view. Ahead of us, looking outward through the thinner outer disk, we can see farther, catching glimpses of other galaxies beyond the Milky Way. This position isn't a point on a flat map. It's a place in three-dimensional space with specific properties in every direction. The density of stars around us, the thickness of the dust between us and the galactic center, the proximity to star-forming regions, the height above the midplane, the composition of the local interstellar medium, the distance to the nearest major spiral arms. All of these vary depending on exactly where you are in the galaxy, and all of them are specific to our location. Move the solar system a few thousand light years in any direction, and many of these properties would change significantly. Consider what it would be like to view the galaxy from a position in the thick disk, say about 3,000 light years above the midplane. From there, you'd be looking down at the thin disk below you. The dense concentration of stars, gas and dust in the midplane would be visible as a bright band below your position, rather than surrounding you on all sides, as it does from our current location. Above you, the sky would be much emptier, with only sparse halo stars and distant globular clusters visible. You'd have a much clearer view of the galactic center, because you'd be looking down at an angle through less dust rather than looking through the full thickness of the disk. But your local environment would be impoverished compared to ours. There would be very little gas or dust nearby. No molecular clouds, no star-forming regions, no nebulae. The stars around you would be mostly old and dim. It would be a quiet, dark, lonely place, scientifically interesting for its ancient stars and clear views, but lacking the richness and activity that characterize our position in the thin disk. Or consider a position deep in the thick disk on the other side of the galaxy. Say 50,000 light years from the center and 1,000 light years below the midplane. From there, the Milky Way band in your sky would appear shifted. Instead of being a symmetric band across the middle of the sky, it would be displaced upward because you'd be looking up at the midplane from below. The galactic center would be in a completely different part of your sky, and the constellation patterns, if any civilization had named them, would be entirely unrecognizable. The sky would contain fewer bright young stars, because the thick disk has less ongoing star formation. Your local interstellar medium would be thinner, with less gas and dust. Rocky planets with high metallicity, like Earth, would be rarer because the thick disk has lower metallicity overall. Every position in the galaxy offers a different view, a different environment, a different set of conditions. Our particular position in the thin disk, slightly above the midplane, inside the Orion Arm, within the local bubble, 26,000 light years from the center, gives us a very specific combination of these factors. And this specific combination may be far more important than it first appears. Because where we sit in the galaxy isn't just an address, it's a set of conditions that may have been essential for the existence of life on Earth. Our position is not just where we happen to be. It might be where we need to be. Now we know where the solar system sits inside the Milky Way. We've built a three-dimensional picture of our position, 26,000 light years from the galactic center, inside the Orion Arm, within the local bubble, about 50 to 80 light years above the galactic midplane, embedded in the thin disk of a vast spiral galaxy. But there's one more crucial thing to understand about our position, and it changes everything we've discussed so far. We're not standing still. The solar system is moving through the galaxy at tremendous speed, following an orbit around the galactic center that takes hundreds of millions of years to complete. And over the course of that orbit, our position changes. The environment around us changes. The risks we face change. The solar system's location in the Milky Way isn't a fixed address. It's a journey that has been going on for 4.5 billion years, and one that has shaped the history of our planet in ways most people never consider. Let's start with the orbit itself. The Sun orbits the center of the Milky Way at a speed of approximately 230 kilometers per second. That's about 828,000 kilometers per hour. At that speed, you could travel from Earth to the Moon in less than half an hour. You could circle the entire Earth at the equator in less than 3 minutes. It's an extraordinary speed by human standards, vastly faster than anything we've ever built. The Parker Solar Probe, the fastest spacecraft humans have ever constructed, reaches speeds of about 192 kilometers per second at its closest approach to the Sun. The Sun's orbital speed around the galaxy is faster than that, every single second of every single day, year after year, for billions of years. And yet, despite this incredible speed, the galaxy is so enormous that one complete orbit takes roughly 225 to 250 million years. This period is sometimes called a galactic year or a cosmic year. Think about what that means in terms of Earth's history. The last time the Sun was at roughly this same position in its orbit around the galaxy, dinosaurs were just beginning to appear on Earth. The first dinosaurs evolved about 230 million years ago. The supercontinent Pangaea was still intact. The Earth was a completely different world. No flowering plants, no grasses, no mammals as we know them. The continents were arranged in an entirely different configuration, and the Sun was at roughly this point in its galactic orbit. One galactic year before that, about 450 to 500 million years ago, the oceans were already teeming with complex life in the wake of the Cambrian explosion. Trilobites, early fish, and vast coral reefs filled the seas. Life hadn't yet moved onto land. There were no trees, no insects, no vertebrates walking on solid ground. The Earth was an ocean world with barren, lifeless continents. The Sun has completed roughly 18 to 20 orbits around the galaxy since it formed 4.5 billion years ago. That's 18 to 20 galactic years. In all that time, it has traveled a more almost incomprehensible distance. At 230 kilometers per second, over 4.5 billion years, the Sun has traveled an almost incomprehensible distance. Each orbit covers roughly 163,000 light years. Over 18 to 20 orbits, the Sun has traveled a total distance of approximately 3 million light years through space. But because it's moving in a roughly circular orbit, it hasn't gone anywhere in the sense of leaving the galaxy. It's been going around and around the galactic center, lap after lap, for billions of years. The orbit isn't a perfect circle. It's slightly elliptical, meaning the Sun's distance from the galactic center varies somewhat over the course of each orbit. At some points in its orbit, the Sun is slightly closer to the center. At others, slightly farther. The degree of this eccentricity is modest. The Sun's orbit stays within a relatively narrow range of distances from the galactic center, probably varying by no more than about 10 to 15% from its average distance of 26,000 light years. This is consistent with the orbits of most thin disk stars, which tend to be relatively circular compared to the highly eccentric orbits of halo stars. But here's what makes the Sun's orbit through the galaxy so consequential. As the Sun moves along its orbital path, It passes through different regions of the galactic disk. It enters and exits spiral arms. It crosses the galactic midplane repeatedly during its vertical oscillation. It encounters different densities of interstellar material. It passes closer to or farther from regions of active star formation, molecular clouds, and potential supernova sources. The galactic environment the solar system experiences is not constant. It changes over time as the sun moves through different parts of the galaxy, and these changing conditions may have had real effects on Earth. Let's talk about spiral arm crossings. Remember, spiral arms are density waves, regions of enhanced stellar density and active star formation that the sun passes through as it orbits the galaxy. The sun doesn't stay in the Orion Arm permanently. Over the course of millions of years, the sun's orbital motion carries it into and out of spiral arms. The exact timing and frequency of these crossings depends on the difference between the sun's orbital speed and the pattern speed of the spiral arms. The speed at which the density wave itself moves through the disk. If the sun orbits faster than the spiral pattern rotates, it will periodically overtake and pass through the arms. If it orbits slower, the arms will sweep past it. The relationship between the sun's orbital speed and the spiral pattern speed determines how often the sun enters a spiral arm and how long it spends inside one. Estimates vary, but the sun probably passes through a major spiral arm roughly every 100 to 200 million years, spending perhaps 10 to 20 million years inside the arm before emerging on the other side. During these passages, the solar system would be exposed to a different environment. Spiral arms have higher densities of gas and dust. They contain more molecular clouds. They have more massive young stars, which means more supernovae. The radiation environment inside a spiral arm is different from the relatively calm interarm regions. Cosmic ray flux might be higher during arm crossings because supernovae are the primary source of galactic cosmic rays, and supernovae are concentrated in the spiral arms. Some researchers have suggested that spiral arm crossings might correlate with periods of environmental stress on Earth. Higher supernova rates could mean more nearby explosions, which could affect Earth's ozone layer and increase surface ultraviolet radiation. Higher cosmic ray flux could affect cloud formation and climate. Gravitational perturbations from dense molecular clouds could disturb the Oort cloud, sending comets into the inner solar system. These effects would be subtle and would play out over millions of years, but they could potentially leave signatures in the geological and biological record. The evidence for this is mixed. Some studies have found correlations between estimated spiral arm crossing times and ice ages or biodiversity changes. Others have found no significant correlation. The difficulty is that we don't know the sun's past orbital path with high precision. Reconstructing where the sun was millions or billions of years ago requires knowing its current velocity very precisely, and modeling the gravitational field of the galaxy over long time spans, both of which have significant uncertainties. We also don't know the positions and pattern speeds of the spiral arms with enough precision to determine exactly when the sun entered or exited an arm in the distant past. So, the connection between spiral arm crossings and Earth's history remains an open question, one that's fascinating to consider but far from settled. Now let's talk about something that puts our entire position in the galaxy into a different light: the concept of the galactic habitable zone. This is the idea that only certain regions of the galaxy are suitable for the development and long-term survival of complex life. The concept was proposed by the astronomer Guillermo Gonzalez and colleagues in 2001, and it has been refined and debated ever since. The basic idea is straightforward. Life as we know it requires certain conditions. It needs rocky planets made of heavy elements like iron, silicon, oxygen, and carbon. It needs a stable environment free from catastrophic events like nearby supernovae or gamma ray bursts. And it needs enough time for complex life to evolve, which on Earth took roughly 4 billion years. Different regions of the galaxy offer different conditions, and some are much more favorable than others. The inner galaxy, closer to the center, has higher metallicity. Stars there contain more heavy elements because the inner galaxy has had more generations of star formation, each generation enriching the interstellar medium with heavier elements. More heavy elements means more raw material for building rocky planets. So in terms of planet formation, the inner galaxy has an advantage, but the inner galaxy is also more dangerous. The stellar density is much higher. Stars are packed more closely together, which means gravitational disturbances are more frequent. A passing star could perturb a planetary system, disrupting the orbits of planets or sending comets raining inward. Supernovae are more frequent in the inner galaxy because star formation rates are higher. A nearby supernova could sterilize a planet's surface with intense radiation. The supermassive black hole at the center, while currently quiet, has been active in the past and might become active again. During active phases, the radiation from material falling into the black hole could affect planets across a wide region of the inner galaxy. The outer galaxy, far from the center, is much calmer. Stellar densities are lower. Supernovae are less frequent. Gravitational disturbances from passing stars are rarer. But the outer galaxy has a different problem. Metallicity is lower out there. Stars in the outer disk have fewer heavy elements, which means rocky planets are less likely to form. Without rocky planets, life as we know it can't develop. You might have gas giants orbiting metal-poor stars, but you're much less likely to find an Earth-like world. The galactic habitable zone, according to this framework, is the region where conditions are just right. Close enough to the center for sufficient metallicity and rocky planet formation, but far enough from the center to avoid the dangers of high stellar density, frequent supernovae, and proximity to the supermassive black hole. This zone is estimated to lie roughly between about 13,000 and 33,000 light years from the galactic center. And where does the solar system sit? At 26,000 light years from the center, right in the middle of the proposed galactic habitable zone. We're in the sweet spot, close enough for high metallicity and rocky planets, far enough for relative safety and stability. This might not be a coincidence. If the galactic habitable zone is real, then our position in the galaxy might be one of the reasons life exists on Earth. We're in the right place, not just in terms of our distance from the sun or our position in the solar system, but in terms of our position in the galaxy itself. But the galactic habitable zone concept has its critics, and it's important to be honest about the uncertainties. Some astronomers argue that the zone is too loosely defined to be meaningful. The boundaries are fuzzy, the conditions vary enormously even within the proposed zone, and the actual risks from supernovae, while real, might be less severe than early estimates suggested. A supernova would need to be very close, within perhaps 30 to 50 light years, to cause serious damage to a planet's biosphere. Even in the inner galaxy, Supernovae at that distance are rare. The concept is useful as a general framework for thinking about which parts of the galaxy might be more or less favorable for life, but it's not a sharp boundary. There probably isn't a clear line inside which life is possible and outside which it isn't. Instead, there's a gradient. Life is more likely in some regions and less likely in others, with our position being somewhere in the favorable range. There's another aspect of our galactic position that's worth considering, and it relates to something called corrotation. As I mentioned, these spiral arms are density waves that move through the disk at a certain pattern speed. The stars in the disk orbit at a speed that depends on their distance from the center. At some particular distance from the center, the orbital speed of stars exactly matches the pattern speed of the spiral arms. This distance is called the corrotation radius. Stars at the corrotation radius move at the same speed as the spiral pattern. They don't overtake the arms and they don't fall behind them. They essentially stay in the same position relative to the spiral arms indefinitely. Stars inside the corrotation radius orbit faster than the spiral pattern, so they overtake and pass through the arms. Stars outside the corrotation radius orbit slower, so the arms sweep past them. The corrotation radius for the Milky Way is estimated to be roughly 26,000 to 28,000 light-years from the galactic center, and the Sun sits at about 26,000 light-years. This means the Sun might be very close to the corrotation radius. If so, it would spend much less time passing through spiral arms than stars at other distances. It would tend to stay in the interarm region, avoiding the denser, more dangerous environment of the spiral arms for longer periods. This has been proposed as another factor favorable for life. A star near the corrotation radius would experience fewer spiral arm crossings over its lifetime, meaning less exposure to the enhanced supernova rates, molecular cloud encounters, and cosmic ray flux associated with being inside a spiral arm. It would spend more of its time in the quieter interarm environment, where conditions are more stable and less likely to produce catastrophic events. Whether the Sun is truly at or near the corrotation radius is still debated. The corrotation radius depends on the spiral pattern speed, which is not precisely known. Different studies using different methods have produced different estimates. Some place the corrotation radius right at the Sun's position. Others place it somewhat closer to or farther from the galactic center. But the possibility that we're near this special radius adds another layer to the story of our galactic position. It suggests that our location might be not just favorable in a general sense, but specifically favorable in ways that involve the dynamic interaction between our orbit and the galaxy's spiral structure. Let's zoom out from these specifics and consider what our position means in the broadest possible terms. The solar system has been orbiting the galactic center for 4.5 billion years, lap after lap around the galaxy, each one lasting longer than the age of the dinosaurs. It has crossed the galactic midplane dozens of times. It has passed through multiple spiral arms. It has encountered different interstellar environments, different densities of gas and dust, different levels of cosmic radiation. Throughout all of this, life on Earth has persisted. It has been challenged, stressed, and occasionally devastated by mass extinctions, but it has never been completely wiped out. 4 billion years of continuous biological activity, unbroken despite everything the galaxy has thrown at us. This persistence might be partly due to our position. We're in a relatively safe region of the galaxy. We're far enough from the galactic center to avoid its dangers. We're in a spiral structure that's active enough to provide the heavy elements needed for rocky planets and complex chemistry, but calm enough to avoid frequent catastrophic events. We're near the corrotation radius, potentially minimizing our exposure to spiral arm crossings. We're in the thin disk, where conditions favor the formation of sun-like stars with planetary systems, and we're inside the local bubble, a cavity of thin gas that shields us from some of the denser interstellar material that could interact with the outer solar system. None of these factors alone would be sufficient to explain why life exists on Earth. Life depends on countless factors, from the properties of our star to the composition of our planet, to the presence of liquid water, to the stability of our orbit, to the protective effects of our magnetic field and atmosphere. Our galactic position is just one factor among many, but it's a factor that's often overlooked. When people discuss what makes Earth habitable, they usually talk about the solar system, the sun's luminosity, Earth's distance from the sun, the moon's stabilizing effect on our axial tilt, Jupiter's role in deflecting comets. These are all important, but they exist within a galactic context. The type of star we orbit, the composition of our planet, the availability of heavy elements for building rocky worlds. All of these depend on where in the galaxy the solar system formed and where it has traveled since. Our position in the galaxy is part of a chain of conditions that stretches from the largest scales of cosmic structure all the way down to the chemistry of life on Earth. The Big Bang produced hydrogen and helium. The first stars fused these into heavier elements. Those stars exploded, enriching the interstellar medium. New generations of stars formed from this enriched material, creating planetary systems with rocky worlds. The galaxy's spiral structure organized this process, concentrating gas and triggering star formation in the arms. The sun formed in one of these enriched regions, in the right part of the galaxy, at the right distance from the center, with the right metallicity to produce rocky planets. And then it moved through the galaxy for 4.5 billion years, carrying Earth along on a journey through different environments, while life evolved and complexified on our planet's surface. There's something deeply moving about this realization. We tend to think of Earth as isolated, a self-contained world going about its business independently of the galaxy around it. But that's not true. Earth is embedded in the Milky Way. It moves through the galaxy. The galaxy's structure and dynamics have influenced our planet's history in ways we're only beginning to understand. The heavy elements in your body, the iron in your blood, the calcium in your bones, the carbon in every organic molecule that makes up your cells. All of these were forged in stars that exploded billions of years ago in some part of the Milky Way. Those atoms drifted through interstellar space, became part of a molecular cloud, collapsed into the solar nebula, and eventually became part of Earth and part of you. You are literally made of material that has been processed through the Milky Way's stellar cycles. You are a product of the galaxy. And you're here because of where the solar system sits, not at the chaotic, radiation-soaked galactic center, not in the sparse, metal-poor outer disk, not deep inside a major spiral arm surrounded by massive stars ready to explode, but in a moderate, stable, favorably positioned region of the thin disk, in a minor spiral arm, inside a protective bubble of hot gas, slightly above the midplane, near the corrotation radius, at just the right distance from the center for both sufficient metallicity and sufficient safety. This specific position, This precise combination of galactic coordinates and environmental factors is part of the reason you exist. The next time you see that simplified top-down diagram of the Milky Way with the little dot saying, "You are here," you'll know how much it leaves out. You'll know that our position isn't just a spot on a flat map, but a point in three-dimensional space defined by distance from the center, position within a spiral arm, height above the midplane, location within a local interstellar environment, and phase in an ongoing orbital journey around the galactic center. You'll know that this position has depth and complexity that no simple diagram can capture. And you'll know that it matters. Not just as a piece of astronomical trivia, but as a fundamental condition that has shaped the history of our planet and the evolution of life. The Milky Way is our galaxy. It's the structure that contains everything we've ever known. Every star visible in the night sky is part of it. The glowing band of light stretching across a dark sky is its disk. Seen from inside, a river of billions of stars too far away to see individually. We're inside this structure, embedded in it, moving through it. And our specific position within it, the particular combination of galactic coordinates and environmental conditions we occupy, is one of the most underappreciated factors in the story of life on Earth. Understanding where the solar system really sits inside the Milky Way means more than knowing a distance and pointing to a spot on a map. It means understanding the galaxy as a three-dimensional, dynamic, structured environment. It means recognizing that we live in a specific layer of a specific arm at a specific height in a specific local environment, all of which contribute to the conditions that make life on Earth possible. It means appreciating that our position isn't static, but is part of an ongoing orbital journey that has lasted billions of years and will continue for billions more. And it means recognizing that the simple diagram you've seen 100 times, the one with the flat spiral and the little arrow, is just the beginning of a much deeper, much more interesting, and much more consequential story. You are not just on Earth. You are not just in the solar system. You are in the Milky Way, at a specific position within its vast three-dimensional structure. And that position has shaped the history of your planet, the evolution of life, and ultimately, the fact that you are here right now, thinking about your place in the galaxy. Every atom in your body was forged in the nuclear furnaces of stars that lived and died within this galaxy. Every element heavier than hydrogen and helium was created through stellar nucleosynthesis and scattered into the interstellar medium by supernova explosions. The carbon in your cells, the oxygen you breathe, the iron that carries oxygen through your blood, all of it was produced by the Milky Way's stellar cycles over billions of years. You are not a visitor in this galaxy. You are a product of it, made from its materials, shaped by its processes, living in a position within its structure that is uniquely favorable for beings like you to exist. So when you look up at the night sky and see that faint band of light arching overhead, know what you're looking at. You're looking at the disk of the Milky Way from the inside. You're seeing the combined glow of hundreds of billions of stars spread across a structure 100,000 light years wide and only 1,000 to 2,000 light years thick. You're embedded in that structure about 26,000 light years from its center, slightly above its midplane, inside a spiral arm, within a bubble of hot gas, orbiting the galactic center at 230 kilometers per second. You've been on this journey for 4.5 billion years. You have billions more to go. And every moment of that journey, every orbit, Every midplane crossing, every spiral arm passage is part of the story of where you are and why you're here. The Milky Way isn't just a picture in a textbook. It's the place where you live, and your address within it, your true, three-dimensional, dynamic, evolving address, is far more interesting, far more specific, and far more consequential than any flat diagram could ever show. The next time someone asks where the solar system sits inside the Milky Way, you won't point to a dot on a map. You'll describe a position in three-dimensional space, embedded in a layered, structured, evolving galaxy, defined by distance, height, arm membership, local environment, orbital dynamics, and a history stretching back billions of years. And that answer, the real answer, is one of the most extraordinary stories in all of science. Thank you for joining me on this journey through the galaxy. If you found this exploration valuable, a like or subscribe would mean a lot. It helps me keep making these deep explorations of space and our place in it. The next time you look up at that band of light in the night sky, remember what you've learned. You're not looking at a distant object. You're looking at home. And your place within that home is more precisely defined, more deeply consequential, and more beautifully strange than you ever imagined. Sleep well tonight, under the stars of the Milky Way, knowing exactly where you are.